Today we're going to look at 4 laws that relate the quantities that are important in understanding gases. There are 4 things that you can measure that will completely describe for you a sample of a gas. One is how much gas is there. In other words, how many moles of molecules or atoms are there. The second one is pressure. Third one is temperature. And then the fourth one is volume. And we're going to look at laws that link 3 of these, pressure, volume, and temperature, together in 3 separate laws and then one that combines them together. We'll start out by taking a little experimental look at the relationship between pressure and volume.
Well, I have here a vacuum pump. You can see there are a couple of gauges on the top, and there's a hose that comes out of it, and that hose leads to this chamber here. It's not really a chamber right now, it's just a flat platen, just kind of a disc that's got a hole in the middle, and that hole connects to the tube that's outside. I have laying on there right now a syringe, and if you look at this syringe, you can tell that the volume that it's reading is about 4.3 milliliters. What I'm going to do next is put a lid on this chamber. Now the lids fit onto a rubber disc, so it makes a nice seal. And then I'm going to turn on the vacuum pump. In a little bit, I'm going to turn on the vacuum pump. And as I do, we'll watch the syringe change volume. As it's changing volume, I'll call out what the pressure gauge is reading from time to time. The gauge that I'm reading from is actually measuring vacuum. I'm going to call out millimeters of mercury vacuum, which is a way of saying millimeters of mercury less than atmospheric pressure, which we'll assume to be 760 millimeters of mercury. Here we go. $200. $300. $350. $400. $450. And $500.
Let's make a table that has all the measurements from the movie. So I'm going to make a column for pressure, and I'm going to make a column for volume. Now we found that when the pressure was 0 vacuum, in other words 760 torrs, it's going to be pressure in torrs, the volume was 4.6 milliliters. When the pressure was 200 millimeters of vacuum, or 760 minus 200, that would be 560 torrs of pressure, the volume in the syringe was 5.6 milliliters. At negative 300 pressure, in other words 760 minus 300, or 460 torrs, the volume was 7. At minus 350, which would be 410, 710 minus 350 is 410 millimeters of mercury, or 410 torrs of pressure. The volume was 8.1. At minus 400, or 360 pressure, 9.0. At minus 450, which is 310 torrs of pressure, our volume was 10.5. And then the last measurement we made was a little uncertain. It was minus 500, which would put us at 260 torrs, 760 minus 500. And it looked like the volume was about 12.3, although we were off the scale, so it might be a little hard to tell. Now, here's what I'm going to do. I want to make a graph that puts pressure here and volume here and see what it looks like. I'll do this with the graphing calculator. First, I need to put all this data into a list. So I'll clear my calculator out, remove everything from my lists, and go into the stat editor. Here in list 1 I'm going to put my pressures. So I'll just key those in. 760, 560, 460, 410, 360, 310, and the last pressure we recorded was 260 torrs. In list 2 I'm going to put the corresponding volumes. So 4.6 at 760, 5.6, 7.0, 8.1, 9.0, 10.5, and 12.3. So now I have a set of volume and pressure data. I'm going to make a stat plot and just see what that looks like. I go second function, get my stat plots up here. I'll turn this first one on. I'll make sure it's a scatter plot. And on the x-axis I want to put pressure, and pressure was in list 1. So I'll do second function 1, put list 1 in there. And then on the y-axis I want volume. So second function 2 puts list 2 in there. I'm going to do a zoom number 9 to get a stat plot. And this is what it looks like. It doesn't look very much like a straight line. Let's do a regression analysis to be sure. So I'll do stat, calculation. Option 4 is linear regression. And on the x-axis I have list 1, so I'll do second function 1, then a comma. After the comma comes what's on the y-axis, which is volume, and that's list 2, so second function L2. Now I'm going to paste that into the graph after I find my correlation here. So I'll click variables, y variables, function, and I'll select y1. Now when I hit enter, I get my information. The r squared value is 0.877, which isn't real good. So this indicates that it's not much of a straight line. But look at the graph. That also shows this is not much of a straight line. Those points don't line up very well on that straight line. So we don't have a linear relationship here. In fact, what we have is a graph that looks like that. Now, there are a bunch of different mathematical relationships that have that general shape. One of the ways that we can test and find out which one we have is by doing this. If we take the inverse of pressure and plot that on the x-axis, and on the y-axis put our other variable, volume, if we find that we have a straight line here, well then we know that the relationship that we have is what we call an inversely proportional relationship. Let's test and find out. So I'll go back to my stat editor. In list 3, I'm going to place the inverse of all the pressures. So I'll just hit L1 and hit its inverse, L1 to the minus 1. In other words, 1 over L1. So every pressure now has its inverse in list 3. Let's make a new stat plot. Go to my stat plot, plot number 1, and I still want a scatter diagram, but now I want my x-list not to be L1 but to be instead L3. So I'll hit second function 3 and change that, and I'm going to do a zoom number 9 to take a look at my plot. Well, this looks a lot more like a straight line. Let's check by doing a calculation. Zoom, calc, do a linear regression. Now my x-axis is going to be L3, so I'll put L3, comma, L2, that's volume, and then I'll paste this into a variable so we can see it on the graph. Now when we do regression analysis, we get a much better r squared, 0.996. Very good. That's indicating this really is a straight line relationship. Let's take a look at the shape of it on the graph. Really nice. The points lie right on the line. So what this is telling us is there is a straight line relationship between volume and the inverse of pressure. There's actually a name for what we just discovered there. It's called Boyles Law. Boyles Law says the volume of a fixed quantity of gas, so that means it's in a container that doesn't leak, no gas is going in or going out, at a constant temperature, that means the temperature doesn't change, varies inversely with the applied pressure. So pressure goes up, volume will go down, as we saw. Pressure goes down, volume will go up. Graphically, here's what we saw. We saw that when we plotted pressure versus volume, we get this downward sloping curve. We also found that when we plotted the inverse of pressure against volume, we got a straight line relationship. Well, straight lines have the equation y equals mx plus b. b here turns out to be 0, so that simplifies to y equals mx. And on the y-axis, it's volume. The slope of this line is a constant. We're going to call it k. That's just the slope of this line is all that is. And then what's on the x-axis is the inverse of pressure. That's what we call an inverse proportionality. So mathematically, we can express Boyles' law this way. We can say volume is equal to a constant number, the slope of a line, times the inverse of pressure. What's really convenient in these gas laws is having a two-point form so we can compare two different conditions for the same gas. Let's take a look at this for Boyles' law. Imagine this shape of the curve, pressure versus volume, this downward slope. What this curve represents is a constant temperature sample of a gas. Any point that lies on this curve represents the same gas at the same temperature, but just under a different pressure and volume condition. So let's say we have condition number 1, where the pressure is P1, and the volume that corresponds to that is, we'll call it V1. And here's condition number 2 on the same curve, so the temperature and the number of moles of gas hasn't changed. P2 is our pressure at point 2, and V2 is the volume at point 2. If we have the relationship that says volume is equal to a constant number times 1 over pressure, and we do a little algebra to that, multiply both sides by P, we find that P will cancel out, and we get this relationship. Pressure times volume is constant. It doesn't change. So the product of any pressure and the volume that corresponds to that pressure is always the same. So that means at condition number 1, we've got P1 times V1, and that's equal to that constant number. At condition number 2, we have P2 times V2 is equal to the same constant number. Well, we take those two things together, and that means that P1 times V1 is equal to P2 times V2. And that is the two-point form of Boyles' law. And it's very handy in solving problems. Like this one, for example. This says the volume of a balloon is 0.750 liters. The pressure is 760 torr. What is the volume of the balloon at a pressure of 350 torrs if it's at the same temperature? Well, applying Boyles' law to this, we can say P1 V1 is P2 V2. What we're trying to find here is what is the volume. So it's the second volume we're looking for. We'll solve this equation for the second volume. Divide both sides by P2 and you'll get the equation for that. So this tells us that V2 is equal to P1 times V1 divided by P2. So let's plug numbers in there. The first pressure was 760 torrs. The first volume is 0.750 liters. The second pressure is 350 torrs. You can see that torrs are going to drop out of this calculation, and our answer is going to be liters, and that's good because that's a volume. When you do the calculation, you find out that it's 1.6 liters, the two significant figures. Why would there be two significant figures? 760 torr and 350 torr have only two sig figs here. You try this one. Stop the video, work it out, and then I'll give you a solution. Well, in this situation, we could set it up this way. We could say pressure on the mountain times volume on the mountain is equal to pressure at sea level times volume at sea level. What we're trying to find here is the pressure at the top of the mountain. That's the variable we're trying to solve for. So we'll isolate it by dividing both sides by volume on the mountain. And that gives us this equation. Pressure on the mountain is pressure at sea level times volume at sea level divided by volume on the mountain. So now we put numbers in there. Pressure at sea level was 760 torrs. The volume at sea level was 500 milliliters. The volume on the mountain was 0.750 milliliters. And so milliliters drop out, and now we're going to get a pressure unit, which is good because that's what we're solving for. Do the arithmetic, you find out you have 507 torrs. 6 things might be off there. I want to show you a real-life example of this from a vacation that I was on. Here's me, you can see my face there, and my daughter and my son. We have hiked to a tea house that's high in the Canadian Rockies, and look at this water bottle here. And look at this water bottle here. That water bottle we had put in our backpack, carried up to the top of this mountain, and we're eating at this tea house that kind of remotely located way up near the top of a mountain. Look at the size of the bottle. It's a normal, ordinary 1-liter bottle. Now, that day, we screwed the lid on the bottle like you normally would. I threw it in my backpack. We hiked down to the bottom of the mountain and got in our car, and we drove from that mountain overnight, and we ended up in Vancouver, which is at sea level. Didn't think about the bottle. Watch what happened when we got to Vancouver. So here's my son, Nils, standing in front of the North Vancouver Hotel. So we're at sea level. Vancouver is a city that's right on the ocean, on the Pacific Ocean. And look at what's happened to the bottle. See the indented side there? It collapsed. It collapsed because the pressure was high inside and the pressure was low outside. So what happened to the volume? The volume of the bottle got smaller because the pressure on the bottle dropped. Here's a close-up. You can see this 1-liter bottle is now clearly less than a liter because of the lowered pressure.